same point where no, I stopped yesterday. Yeah. So just I'll put. I think most of you have joined. Okay, let me start. So yes, just I will try to draw the graph that I shown yesterday so that you can notice the change at 8 in instant. Okay, so with the help of this slate, so this was our I'll put in more, sorry. Yes. Okay, so yeah, here is a pen. Just I'll try to complete this diagram, this graph. So I'll say, no, this is my, sorry, anode current, and on the y-axis, x-axis, I have VAK. Okay, and no, we have seen the change in the current, that is from 0 instant. If you start the current slowly, it increases, and as soon as your device turns on, this is what the characteristics graph you are getting. This we call it as VBO. Breakover voltage point is this. We have seen this in the beginning. Up to breakover voltage, whatever graph I have shown for a current, small variation in the current, small increase in the current, that is a that is leakage current we call. Leakage current is a current which is flowing in the device when a device is in off state. Up to VBO, your device is in off state. Simple. It is forward biased device, but not conducting up to VBO. Hope you understand this point. And once it turns on, suddenly there is a change in the voltage across the device. Suddenly it falls to somewhere. This is a dotted line. I'll try to show maybe VBO. If it is 10 volts, suppose say 10 volts. Okay, maybe here 0.9. This is a dotted line what I have shown. It falls, the voltage across SCR falls to 0.9 volts. For example, I have taken, maybe it is 0.8. Okay, a small difference will be there device to device. So this is how we got a latching current as soon as you turn on the device. So I'll call this is latching current. So latching current point is, this is a latching current point. Okay, right. So now you can just vary the VAK on x-axis from 0.9 to 0.95, just 0.05 volts, small voltage. You try to vary, you will get sudden rise in the current. Suddenly, even for 0.05 volts, very small negligible value, millivolts makes a big difference in the current rise. So current reaches to some value here for maybe 0.1 volt difference on the x-axis, maybe 0.9 to 1 volt variation. I am getting this vertical line, and I called it as forward conduction region, or forward conduction mode of operation. Okay, so I am using this slate today itself, so I am not very much familiar, so I'll go a little slow. Yes, region, and this region we call it as forward blocking mode of operation or forward blocking region, okay, of this SCR. Okay. So now you have seen the forward conduction, and slowly you want to see the turnoff process also. That's why you are decreasing VAK on the x-axis and your current starts falling like this. Are you able to see Sunil and Abhishek Gowda? Ananya?
Yes, sir. So we can see, sir.
Yes. Now,
Yes, sir.
yes, I have started the turnoff process. Once you see the conduction, we'll see turnoff process. Now you are decreasing VAK, your current also starts falling like this. It may come here by just changing the voltage by 2 volts. Yes, again 2 volts. If you change, the current may come to this, and one state of voltage VAK, current will reach the latching current. After that, you should be very careful in operation just to see the turnoff point from which current value your device goes off. Just to observe that, you should be careful that otherwise you will not be able to observe that point, holding current point, and you will not be able to tell what is a holding current. In the exam also you have this experiment. That's why only PPT I did not say that completed. I have explained this, but I am repeating. This will, with each stage, what is happening. If you get the point, then it will help in your laboratory in the exam. Yes, latching current you are noting down as a result part. Breakover voltage you are noting down as a result at which your device is turning on. Holding current magnitude also you have to write in the exam. So that's why I'm telling with this diagram. Yes. So that variation can be observed. Now, once you observe latching current, slowly, maybe 0.05 volts, small change in the VAK you make, you see the current may fall to this. Maybe latching current time being, you assume it is latching current in the beginning when it turns on, milliamperes of current. Okay. So now your current is decreasing as you are decreasing further VAK. Your current is decreasing from 10 milliamps to 5, maybe here 5, maybe here 4 milliamps, and after 4 milliamps, if you try to reduce VAK, suddenly it falls to 0. Suddenly the current falls to 0. This point dotted I will show. I will not show because you will not be able to see this variation at all. From 4 milliamps directly it falls to 0. So 4 milliamps is a holding current. That is how I label holding current I suffix H. Holding current 4 milliamps. 4 milliamps. Okay, 4 milliamps. So this is the process, turn on process as well as turn off process. Both you are observing in the device. That's why I call this device is meant for switching operation, switching purpose. Same device connected anti-parallelly. Two devices connected anti-parallelly can work as a perfect switch for your AC supply connected to the fan, and you can replace your existing regulators in the home and offices that you are wearing. Regulator you are wearing, and you are varying the speed of the fan, right? All of you agree. You vary the speed of a fan by varying the regulator knob, right? Position of the regulator knob in the home, right? So in that regulator, see, in old regulators you will find rheostatic, that is resistive control mechanism, where you are varying the resistance value and varying the voltage that is going to the fan. Inside fan, what is there? Motor, no? AC motor, correct? So that AC motor speed can be controlled by varying the resistance. That was an old method. In old regulators you will find resistive mechanism for varying the voltage. Today you will find SCR based, triac based. Triac is nothing but SCR, but both bidirectional device. Triac is. SCR is unidirectional device. Okay, same SCR, two SCRs I can take and I can build a triac device, and I can use in my regulator. And no, why two bidirectional device I want? Can Ananya say something? Nikita.
Yes, sir.
Why I'm talking about triac? SCR is a unidirectional device, I said. Triac is bidirectional device, I said. Both are same. See, but two SCRs connected in parallel in opposite direction forms, or it becomes a triac structure. So SCR, if you know, triac is nothing. Okay, so in our regulator people use triac. Why not SCR? Because SCR connects only in one direction, and your AC has got, right, positive, it goes positive cycle, negative cycle, right? So you want a device which can conduct for positive half cycle as well as negative half cycle, correct? No?
Yes. Yes.
Yeah, in your homes, when you connect a fan to your power unit, power point, the supply, AC supply is going to the fan motor, because you are inside a fan, you have AC motor. So that will work on AC supply. Okay, so yes, so you need to turn on that fan in both the direction, right? So that is continuously you should be able to vary the speed. To vary the speed, again, gate triggering technique you are using in the that regulator. That detailed discussion I will not do because it is confusing at your level, third sum level. So, but those who are interested can discuss these points and build small projects in the laboratory once you come back to college. Physically, when you conduct experiment in the laboratory, small projects like this, that will excite you. Okay, that will motivate you in building electronic circuit, and you will not say electronics is tough. Okay, so definitely we can explore this. We can try this in half an hour. If you spend in the laboratory, I will guide you to build these small circuitries. Okay, so next, turn on and turn off process we have seen. Next, if you apply, see what is the previous circuit? What is the previous circuit? What I was talking? Yes. Are you able to see when gate is positive with respect to cathode slide?
Yes, sir.
Okay, good. So to observe the device behavior during negative, with respect to negative supply means this V what I have shown in the battery voltage V what I have shown here, I will just reverse the polarity of that battery and apply across the same circuitry. I will not change gate pulse, I will not change the direction of the device SCR, I will only reverse the battery polarity. And how my device behaves, let me check. Okay, so my device, how it behaves, I'll try to explain you. See, from this zero instant, you are applying a negative battery voltage across SCR. What happens to SCR state? What is the state of SCR? Abhishek Gowda? Neeraj?
Yes, sir.
Yes. When I have applied the battery, that is negative voltage to the SCR, what will happen? How it behaves? Can you explain me? What are the junctions that are forward biased? What are the junctions that are reverse biased here?
Yes, so when you give a negative voltage to the SCR, junctions
Yes.
J1 and J3 become reverse bias, while
Very good,
J2
very good.
becomes forward bias. Because of
Yes.
that, the current does not flow, the SCR drops into the
Yes,
off
yes, very
state.
correct, very correct, very good. That is what, at least you should speak. Yes, you are trying and you have answered. Good. So when you reverse bias this, J1 and J3, two junctions are reverse biased. Only J2 is forward biased actually. And if you further increase that reverse voltage, at one reverse voltage maybe minus 10 minus 20 volts, for example I'm taking minus 20 volts, your device junction J1 and J2 may break down, and sudden rise in the current you can observe like this vertically down, what line I have shown here in the graph that says suddenly there is a rise in the current. Y-axis is current, right? So reverse current can flow in the device, but that is not useful for us because it may damage the negative higher voltage, may damage the device, it may burn the device. We call it as a breakdown of the device, this point. So breakover voltage you can call minus 20 as a breakover voltage, reverse breakover voltage, reverse breakover voltage, whereas this is forward breakover voltage, VBO, what we discussed yesterday and today in the beginning. VBO is a forward breakover voltage, but this you can say reverse breakover voltage, VBO. Okay, so I am interested in forward biased condition, forward conduction of the SCR, not reverse biased case, because that may damage the device. With high reverse voltage, negative voltage, there are chances that device may goes off, and it is of no use. Only I am using this as a unidirectional switch, perfect switch. It works fine for me for my all applications. So I need not worry much about the reverse bias condition. But in the graph, when you write the graph, try to show this. Okay, so fine, good. So yeah, this is impact of that trigger pulse, what I was talking, triggering or gate pulse, what I was talking yesterday. When you apply the gate pulse, are you able to see the waveform animation?
Yes, sir.
Either you consider first graph or a second one. Just I took a second one because it is labeled with voltage. So anode cathode voltage, your output what you are getting, but how you can vary the output by applying the gate voltage VZ. At the bottom you can see, if you want to consider first waveform, this blue colored pulse is a trigger pulse or it is a gate pulse what you are applying. So if you apply the gate pulse in the beginning at 0 reference, conduction will be full. From 0 to pi you will get the output. If the trigger pulse applied, gate pulse applied is delayed, something like this, the output will decrease. You can see this, yes. So that is the effect of gate pulse. Gate pulse output can be varied. The point you observe here is you can vary the output. Don't worry much, because I'll be discussing again in the subsequent chapters full of this applying the trigger pulse and waveform variation. You can observe this again and again, but with the different loads, resistive load, inductive load, and all. We'll discuss. Even we can consider motor as a load, and we try to analyze the circuitry, and we can write the waveforms. Okay, so this is the beauty of this trigger pulse, that is gate pulse. You have better control over the output, and that is why the naming is done silicon controlled rectifier. It is not just a rectifier, it is controlled rectifier. Why? Because you are able to control the output fully. Okay, just you have to change the triggering angle alpha, what we use here frequently. Alpha, if it is 30 degree, your conduction angle you can observe at the output from 30 degree. If you turn on at 90 degree, yes, exactly half of this rectified wave what you are getting, exactly half will be available from 90 degree to 180 degree. Yes, so that is how by varying the triggering angle, varying the pulse or delaying the applied pulse will vary the voltage at the output. So one best example, thus practical application I have taken here, how your SCR works and how you apply the trigger pulse or gate pulse for this SCR and how you know operate this. Maybe you can connect a simple buzzer which makes a sound, okay, which produces sound with the help of this SCR. Can you see the thyristor at the bottom? Thyristor is a SCR only. So you have a diode like structure here, which is thyristor, which is nothing but thyristor or SCR you can call, and gate terminal you can observe. Okay, the register 1K left hand side horizontally connected register 1K is connected to SCR gate terminal. That itself is a gate. Gate pulse is coming through this 1K register from the left side. So you have two wires here, two wire loop on the top, and wire course at the below that. Okay, when there is a closed path for the current flow, when this wires are connected shorted, there is a flow of current. When that wires are connected, when you switch on the switch here on the right hand side, power switch, you can see in the homes you have switch like this, right? When you connect, just press the switch, there is a connected, the wire gets connected to the circuitry, and circuit is completed. There is a path for the current flow, and that current, okay, that current, what it does, it makes contact that you are operating, sorry, this left hand side what you have shown here, two wires get connected and completes the loop, and there is a path for the current flow. So there is two mechanisms here. One is your supply is coming from the right hand side. You have two terminals at the bottom, which is horizontally connected red line is a yeah, when it is on and current is flowing, it shows it is off. Okay, no supply because it is open. Switch is off and switch is on, both the status you can observe. What happens when switch is on? Supply is available across this thyristor between anode and cathode, but anode is connected to the buzzer and then to the switch, no doubt. Yes, but anode is connected through the buzzer to the switch only. Whenever switch is closed, the supply comes across SCR, and also gate pulse comes at the gate of SCR. So SCR is forward biased, and with application of gate pulse, your SCR turns on, and there is a path for the current flow from the switch to the buzzer to the SCR, and then to the that completes the loop. Right hand side, I have shown it is open, but that is a battery that you can say it is a supply what you are feeding. Okay, it is not shown here. I tried to find out correct practical circuitry. This is what I got, but I think you will understand one practical application, how I can make use of this SCR in reality, in practice. Okay, and you can just make buzzer sound whenever there is a current flow in the circuitry. Okay, buzzer produces sound. So simple circuitry, it is one switch and one SCR and buzzer to give you sound. Okay, whenever there is a close, when you turn on the switch, there is a path for the current flow, and you get your SCR turned on, and buzzer makes sound. Okay, so this is the best practical application you can build in the laboratory at third sem level. Then I will tell you some application like night lamp, building a automatic night lamp and all with the same concept. Okay, same SCR, or even with one more circuitry IC 555 timer, I can demonstrate to you in the later part of this semester okay, discussions. Okay, so this finally I want to conclude about SCR. I have covered fully. I have discussed the characteristics in detail. It's a different mode of operations and how you can write the circuitry for the circuit and structure for SCR. The following conclusions, sorry. Yes, 1 second. Let me check whether I'm recording. Yes, I'm recording. This big difficulty. I forgot. Yeah. So, what are the conclusion you can draw? SCR has two states. Either it conducts or doesn't conduct. So, it can work as a perfect switch, on switch and off switch. So, whenever it conducts heavy current, and there is no state in between, only either off or on. That's why we say SCR behaves like a perfect switch. So there are two ways to turn on SCR majorly that are used in practice. First method is to keep the gate open and make the supply voltage that is equal to breakover voltage and turn on the SCR. Correct? Now we have seen this. So second method, what you do? You apply the trigger pulse and turn on the SCR. That time your breakover voltage will vary. That is, it will be less than the previous value. Breakover voltage will be less in the second case when you apply the trigger pulse, that we have seen.
Sir, but the
Yes.
first method you told, if you keep the gate open and put the supply voltage, it will heat the device a lot, right?
Yes, correct, very correct. Because see, when you say gate is open means gate pulse is or gate voltage is absent. Simple. When you do that, when you don't apply gate pulse or gate voltage, there is no gate current flowing in the device, and your device J2 junction is reverse bias, and to break down that J2 junction, you have to apply higher voltage. When you apply higher voltage, definitely device will get more heated and more power loss in the switching action of the device.
Yes.
Right? That's good. Anything else? Any doubt? Others? Yes. So third point, what I'd like to tell here is applying small positive voltage to the gate is the normal way to turn on SCR. Means what? This is a regular practice people use in reality, in practice. Okay. How? Applying gate pulse, gate voltage, they turn on the device. That is a normal practice, what I am trying to convey with the third point. Okay. You don't usually keep gate open and then apply high voltage and see the operation of device. No, that is possible, but it is not used widely. Okay, not used much in practice. So to turn off SCR, to make it non-conducting device, what do you do? Reduce the supply applied across the SCR until 0. You try to go, you will go on reducing. So that is what a few few conclusion points we can have on SCR. So in continuation with this, next part is gate characteristics, gate turn on methods and turn off methods. That completes the discussion on SCR. So turn on methods I'll try to discuss. Gate characteristics, again, region of how different curves in this graph, what they indicate and all, I will discuss at the end, because not to confuse you at this stage, just I will go to directly SCR triggering methods. SCR turn on methods are called triggering methods. Don't get confused. SCR turn on methods or triggering methods, one and the same. Hope you are following. These are the methods people have explored to turn on the SCR. Just to turn on, not turn off, only turn on. That's why I call these methods as turn on methods or triggering methods, or even you can call these methods as firing methods. SCR firing methods. Firing is turning on the device, SCR. So don't get confused with the words that, terms that I use. Firing, triggering, turn on. Okay. So yes, first method. What is the first method we can discuss? Any guesses? Same thing. This is one method already we have discussed. Two methods we have discussed actually. Right? What is that? Apply the voltage and turn on the device. No gate voltage. That is a forward voltage triggering. Some textbook, they say forward voltage triggering mechanism or method, or forward voltage method of turning on the SCR. Yes, no doubt in this. So I will not discuss again repeatedly, because you are applying the voltage across anode and cathode, and you know very well that J1 and J3 are forward bias and J2 is reverse bias. So but it takes more voltage to turn on. That's why this method is not preferred, as no current flows due to the depletion region in J2 junction, which is reverse bias. Or whatever small current that flows in the forward blocking state of a device, we call it as a leakage current, right? But if you increase the voltage applied, J2 junction breaks down and you can observe the current flow, and it is possible to turn on the device, but not preferred method. Correct? No need to discuss again and again, right? So this method also we discussed, but I have taken it as a separate turn on method, because in the exam it will be asked, discuss turn on methods of SCR. 8 marks. 4 methods you discuss in a paragraph with wherever it is possible to write a diagram, write. At least you write the SCR characteristics and try to explain. Gate triggering. What it is? Can anybody? Yes, Anupam? Ankit? Anirudh?
Yes, sir.
Yes. Gate turning. As soon as you see this level, you should be able to explain, because already we discussed this. Same write-up discussion theory I have written here. Okay. So gate triggering, which this thyristor will get forward by this will be turned on at breaker voltage, some breaker voltage that you can observe practically. So if the device is taking 10 volts to turn on without a gate pulse or gate voltage, it may turn on at 3 volts or 4 volts when you apply the some gate current, like maybe 5 milliamps or 10 milliamps. Okay, so that is the advantage of gate triggering. You can avoid overheating of the device by turning on device at lower breaker voltage. Very simple. So higher the gate current if you apply, lower the breaker voltage that the device takes to turn on. Okay, so why it happens? So when positive gate current is applied, last but one paragraph I am just going through, the gate, when you apply positive gate current at the P layer of this SCR structure, hope everybody can recall SCR structure, 4 layer PN. So the second P layer is applied with a gate current, and it is flooded with electrons when you apply the gate current. Okay, so and as cathode N layer is also heavily doped compared to P layer, the width of a depletion layer is reduced. The width of a depletion layer around the junction J2 gets reduced. Okay, so that is why junction J2 breaks down at this breaker voltage and the gate current. So if the magnitude of the gate current is further increased, more and more electrons will reach J2 junction, and that will turn on the device. We have seen this, but detailed discussion is done here. Okay, so gate triggering mechanism, whenever they ask you, please write the characteristics graph like this, showing that at a different gate currents you will have a different breaker voltages. So this is a must. Yes, all of you listen here. This point I have asked in the last class, one question. VI characteristics of SCR. Gate effect. See, when I ask this IZ is equal to 0, IZ1, IZ2. 3 points, 3 gate currents I have shown here. So at each gate current, your breaker voltage will change. It is reducing as you increase the gate current. So that point you should be able to discuss. You should be able to show in the graph as well. That is very important. Don't show one point. Okay, gate current. 3 curves you can show like this. 1, 2nd, and 3rd. Okay, so that will tell the evaluator or examiner that yes, you know the impact or importance of gate pulse and magnitude of the gate current. If you vary, there is a variation in the breakover voltage and there is a variation in the conduction of the current in the device. So you can see that variation in this characteristics curve. Next is pulse gate triggering. What I was talking, gate pulse triggering, that is a voltage applied at the gate, but the similar technique only, but you are not giving a single voltage and once you are applying the pulse, you are applying a train of pulses or you are applying a sequence of pulses continuously. So what you are trying to do is, 1 second. So what you are trying to do is, you are maybe building a simple circuitry, oscillator circuitry, which is generating a pulses, square pulses continuously, and those pulses are interfaced with the gate of a SCR. Okay, and you are passing the pulses one by one after periodic. It is periodically done. The pulses are moving to gate after regular interval of time. So that is how you are applying the pulse. You are turning on the device, again applying the next. You are leaving some delay. Okay, after some delay again you are turning on. So it is a continuous train of pulses that you are applying at the gate of SCR, and you are making sure that even if the first pulse doesn't make no difference in the conduction of SCR, if it misses or it fails, I can say, if one pulse fails to turn on the device, next pulse will turn on the device. So that is how continuous pulses are passed through gate of a SCR, right? So that is a mechanism. It is similar to your gate triggering mechanism only, but pulse gate triggering is train of pulses or a sequence of high frequency pulses you are passing. So that is the only difference. So this is a method which is used widely, and gate triggering is also used. Train of pulses, it's sequence of pulses. Okay, so advantages of this also I have noted here. As you are applying the gate pulses continuously, as I said already, if previous pulse fails to turn on the device, next pulse will be there to turn on it automatically. That's why you are passing train of pulse. So low gate dissipation at higher gate current. So with this, it is possible to keep the device within the limit of power dissipation. So because you are turning on the device at lower voltages by applying the gate pulses, so power dissipation in the device will be less. Yes. Yes, sorry. Yeah. When the first trigger pulse fails to trigger SCR, the following pulses can succeed in latching SCR. Latching is also called turning on SCR. So this is one mechanism. One more mechanism of turning on SCR is this. Please read, maybe I'll ask Ananya MS.
Yes, sir.
Can you just read out this slide? dV by dt triggering. Yes, I will ask question on this at the end of this session. Another 5 minutes, I'll stop and I'll ask question on this, whatever I have discussed today, and just all others listen. Ananya will read now. Yes. Go ahead, ma. Yes, Ananya MS.
dV by dt triggering with a
Yes.
forward voltage across anode and cathode of a thyristor. Two outer junction A and C are forward biased, but the inner junction J2 is reverse biased. The reverse biased junction J2 behaves like a capacitor because of the space charge present there. As a PN
Yes,
junction
yes,
has capacitance,
one
so
second.
larger the junction area, the larger the capacitance. If a voltage ramp is applied across the anode,
Yeah, go ahead now, go ahead.
if a voltage ramp is applied across the anode to cathode, a current will flow in the device to charge the device capacitance according to the relation IC equal to C into dV by dt. If the charging current becomes large enough, density of the moving current carriers in the device induces a switch on. This method of triggering is not desirable because high charging current IC may damage the thyristor.
Yes, good. Yeah, what is the message you are drawing here is, hello, you just recall SCR structure. So you have three junctions, J1, J2 and J3. We have seen this and we have discussed many times, but many times we are repeating this, but with respect to different triggering techniques we are discussing. Okay, so these triggering techniques, gate triggering, pulse triggering, forward voltage triggering, this dV by dt triggering, temperature triggering, one more technique I will tell you after this. So these are the methods available to turn on the SCR. Very clear. Okay, but the best one is gate triggering and even pulse of train of pulses continuously when you apply, that will have better impact. So whenever you require no system where you are operating a system in a process industry and you want your system to continuously run, and if you want to have control over the output there, so continuous pulses, the train of pulses, what I said, are a method is preferred. Okay, so and if you are trying only one device at a time and you are checking the behavior and a simple application, just turn on and then turn off, then that mechanism, your gate triggering, one pulse applying and just okay, turning on maybe a bulb or so, that will suffice, or that will help you to understand simple application. But this is one more method people have explored, people have tried, but what is the impact of this? Just let us see. A reverse bias junction J2 behaves like a capacitor. See, when I say junction is reverse bias, meaning is there is an open circuit, right, between these two layers of the device, because device is not getting the path for the current flow, means there it is like open circuit. When you say open circuit, the reverse bias junction acts like a capacitor. Capacitor has got two plates, positive plate and negative plate, and in between there is no physical contact between the two plates, only it is a dielectric medium is available between the two plates of capacitor, correct? No, yeah. So that is how it is explained here with no detailed discussion what exactly is happening when it is reverse bias. So when J2 junction is reverse bias, because of the space, it is acting as a capacitor because of the space charge present there, space charge in the dielectric medium that is present there. PN junction has a capacitance, so larger the junction area, larger the capacitance, right? So if voltage is applied across this anode cathode junction of diode or SCR, sorry, a current will flow in the device to charge the device capacitance. And how it will charge? With what relation? This is a relation. I see the current in the capacitor is C into dV by dt. You are applying the voltage VAK across the device, right? We have seen, right? Yes, that is a voltage. But that voltage you are varying with the time. dV by dt is that voltage varying with the time. So as you are varying the voltage, definitely capacitance will also vary. The current will vary. The charging period will vary in the this junction area. So that is a mechanism what is discussed here, dV by dt triggering with application of voltage VAK. You are turning on the device, but what is happening in the J2 junction, that is explained here in detail. Okay, so if charging current becomes large enough, density of moving carriers in the device turns on the device. Okay, meaning is, as your capacitor is getting charged for the applied voltage, and once it will reach a stage where sufficient carriers are accumulated in the junction, and it will turn on the device. That is, your J2 junction breaks down. That is what indirectly I am trying to convey. So this method is not desirable, as high current, charging current may damage your SCR or a thyristor. That is only a problem, okay, here in this case. So light triggering is also possible. In place of gate terminal, right hand side you can see the structure of SCR, and gate pulse P layer is applied with a light. Instead of gate pulse, gate voltage, you can apply light and turn on this SCR device. So what exactly happens is, light particles called photons, they strike the junction, right? So which causes the increase in the electrons number and hole pair combination, hole electron pair combination, and this light triggering mechanism for SCR is applied in the inner layer of P layer. Okay, so that provision is done in the fabrication process itself. You may not understand, just you understand that there is a method of light triggering, or there is a method to turn on the SCR by light, or light, with the help of light you can turn on the SCR. That possibility is also there. So what you do here is pulse light of appropriate wavelength you choose, and that is guided by optical fiber for irradiation, that is applied here, okay, with the proper arrangement and proper structure creation, and by guiding with the optical fiber. That light is guided by optical fiber, and it is applied on this P layer of the device, and it is turned on. Okay, so that will turn on the SCR. This is also not used in a regular application, but it is used in a high voltage direct HVDC transmission systems. Okay, so light activated SCR is also in place. So in application like HVDC, what we call high voltage direct current, HVDC transmission, HVDC systems in power transmission and all, they use this mechanism. Otherwise, in other regular application, we don't use this, as it requires the facility to create the structure and then apply proper light at the layer and then turn on. Okay, so these are some of the methods we have for the day. Okay, we have discussed. Next class I will discuss SCR turn off methods, and I'll stop here, as I have to give questions for the writing also. So you have 7 minutes. You can answer any four methods of turn on of a SCR. I have posted a simple question there in the question part of Google Classwork. Just see there, and short answer part you can go and just answer 3 lines each method. So 4 methods I want, any 4 methods of turning on SCR. Okay, so 4 into 3, 12 lines, takes 5 minutes. You just explain in brief and Okay, post that. Okay, so I expect who is sending me attendance?
Aditya, sir.
Yeah, Aditya. Yes, good. We'll stop here. Please go ahead and answer the question. Takes 5 to 7, 8 minutes, not more than that. Complete it fast. You can write a type there itself, your answer, two lines answer. Google Classroom, you go to Google Classwork, and then in question part, I have given the question. Okay, not in the assignment. Okay, so I'll stop here and I'll continue with turn off methods in the next class, and then actual circuit discussion analysis I'll start after that. Okay, so thank you. See you tomorrow.
Thank you, sir.
Right.
Thank you, sir.
Great day, sir.
Thank you. Right.